So we looked at an atom, right? We said protons, neutrons, and electrons. And I went through trying to fish for answers, as I typically do, and asking for what things mean and what they are. Okay? So when I go through and talk about protons, neutrons, and electrons, I try to define them for what they mean. Okay? Not what they are. Like a proton. What would you tell me about a proton? It's a positive charge. Okay? Well, what does a proton mean? What does it define? Okay? It's the identity of the atom. What is an electron? Isn't an electron part of the atom? So why is an electron not defined in the atom? Okay. The electron, okay, I heard someone say, defines the charge. Okay, well, what is charge?
Difference between proton and electron.
Difference between protons and electrons. So if the electron defines the charge, why did you just say protons? Damn it. Yes. Okay. So when I go through and look at these, and I would agree, I think the electron should be described as defining the charge. That's the most important thing that the electron defines. The proton defines the element. Once I know what the element is, I just need to know how many electrons there are to figure out the charge. Okay? So once certain pieces of information are defined, I can then layer on top of that. So then what's the neutron? Well, it doesn't have charge, so it can't define the charge. Does it define the element? No. It defines the mass. Right? Well, but doesn't a proton contribute to the mass? Yeah, just like a proton contributed to the charge, the proton will contribute to mass. Okay? But once I've defined the element, I can change the number of neutrons by adding neutrons in to define the mass. And that's why I come through with these conclusions. Okay? When we looked at Gen Chem, you looked at pretty much all of those back and forth, protons and neutrons being in the nucleus, and then we had electrons being orbitals at the end. Which of those two sets are we going to be most concerned about in OChem? The interior or the exterior? The exterior, which means for the most part, the only thing I'm concerned about is electrons and where they are located. Okay. As I change their location, I can change the bond characteristics of that molecule. Okay. I can change hybridization, I can change shape. Okay. All of that comes from the electrons. Right? So when you went through and did what was the quantum numbers, right? Yeah, everybody loved those quantum numbers. The N, the L, the M sub L, all that. Yeah, we had to memorize all that. Okay? We don't need to memorize that per se. We need to understand what those things mean. What are those shapes and how do those shapes apply outwards? Okay? What are the energy levels of these? How does that change the reactivity? Okay? Where are you happiest? Okay? When you're being dangled by the cuff of strip of your neck 200 feet in the air, or when you're on the ground? You don't have a parachute, by the way. I think 200 feet, it's not going to help anyway. Okay? You're probably a little bit more comfortable on the ground. It's a lower energy state. So when we're looking at our electrons, what we're trying to define is what is their energy. Okay? If their energy is very, very high, that becomes a reactive electron that can then do something. If the energy is very, very low, well, it's not likely to do anything. That doesn't mean I can't make it do something. That just means it's less likely. Okay, so it's a question of manipulating those and seeing what we've got. So our electrons exist in orbitals. Okay? And we've got our orbital diagram, sort of, drawn here, where we start with our nucleus and we go to the first energy level, and the second and the third. Remember how all those things stacked out? Those would be our energy levels. Those are our individual rows on the periodic table. Okay. Awesome, fantastic. Okay. Where does OChem sit as far as those energy levels? Arguably, actually, we should go up one more. That's OChem. Why do I not care about all those? Because that's really hard. Okay. OChem thinks that's too difficult, so we'll keep our focus down on the lower energy levels. So the first energy level, the second energy level, and sometimes we'll get adventurous and move into the third. For the most part, we just sit in that second energy level. Which means I really only need to be worried about 2 electrons, right? Because I can only fit 2 electrons into an individual orbital. But if that was the case, I would only have 14 electrons, right? Which would be 14 elements. So what happened to each of those energy levels? They split into sublevels. And that's why we have the boxes kind of within our periodic table. The first two rows, followed by the transition elements in that block, and then the P block at the end. So recognizing those patterns within the periodic table can help us out. And we placed our electrons into those energy levels after they split. Okay. Where did we start placing our electrons? As a hint, it is bullet number 1, which shouldn't have shown up. My fault for animations. Okay. As a secondary hint, this was review. Hopefully you knew where your first electron goes. Where's your first electron go? The lowest energy level. Why would I place my electron at the lowest energy level? When you came in here, how many of you came in and stood? Just stood. Look around. Feel free to look around. Because a few of you are like, oh, I don't even know how to answer that question. Well, look around. How many of you are standing? Nobody. Okay, why is no one standing?
Well, other than you, you're standing.
I'm standing, yes. Because I clearly have more energy than you, and I need to burn that energy off. I am at a higher reactive state. Okay? I have to somehow, I've been burdened with the effort of trying to get you to learn the material. Okay, so I have to release that energy before I can sit. Okay? We always go to that lowest energy state because that's the least reactive. That is closest to the nucleus. That is where the charge gets canceled. Okay? Where I have a negative close to a positive. Okay? So that's where I start placing the electrons. The next electron goes. Okay. We could go up to the next orbital. I also heard a suggestion go to the exact same orbital. Okay. So if this was my 1s, come on, pen, work with me. My 1s, be simple, just say 1s and 2s. I heard a suggestion that our first electron goes into the 1s because that was our lowest energy. Our next suggestion was we put one up in the 2s. I also heard one in the 1s. Which do we do? Why do we go to the 1s and not the 2s? Lowest in energy. That's why I fill that one. Okay, where's the third one go? Lowest energy, so I should put it in? No, okay, why can't I put it in the 1s now? Why is it full? Why do orbitals only fit 2? It's a charge repulsion. Our electrons are going lowest energy to cancel the charge. Okay? If I add another electron, I'm going to want to cancel that charge, but there's a charge-charge repulsion that I have to counteract. What did our electrons do to account for or minimize that repulsive effect? That was our spin states. They spin opposite directions. Okay? Well, I have a positive direction and a negative direction, which means I have 2 spin states. Okay? I don't have a third, which means each orbital can only hold 2 electrons. If that orbital is now full, I have to place my next electron in the lowest energy available. I can't go into the 1s. That's why I move up in energy to the 2s. So it's a question of slowly transitioning through those electron configurations that you memorized back in 151. Okay? That establishes where our electrons are. Okay? So now we have one there. Where's the next one go? Okay? I heard a suggestion for the 2s. Why does it not go to the 2p? 2s isn't filled, which is getting to bullet number 1, energy. What energy level is the 2s orbital in? As a hint, it's part of the name. 2. Yes, that's what the energy level meant. That's what that number was. What energy level is the 2p orbital? 2. Aren't they the same energy? No. Okay. Notice on the diagram that I've drawn them separate. What happened? When we changed that orbital orientation or the type of sublevel, the energy level split just enough that I can see a difference in energy between the 2s and the 2p. Which means when I put in that 4th electron, it's going to go to the lowest energy first. That's why it's going to go to the 2s instead of going to the 2p. Where's the next electron go? The 2p. Where's the next electron go? The 2p, right? But then it's paired, isn't it? 2p can hold 3. 2p what can hold 3? Define what 2p is. This is again coming back to our terms, like our intersections. 2p orbital? That's me fishing. Fishing for the wrong answer, actually. The 2p orbital can hold 6 electrons? No. The 2p orbital can hold 2 electrons. The 2p shell, okay, which is really referencing the p-type orbitals, can hold 6. Why can they hold 6? Because there's 3 different 2p orbitals. Well, why are there 3 2p orbitals? And there was only one s. Okay, OChem is a lot about shape. What does it look like? Okay, how do those pieces move? Okay, so I heard a suggestion for the p orbital. What did the p orbital look like? Okay, a dumbbell. What does the s orbital look like? A sphere. What are we talking about is a difference between the s and the p. If I take that s orbital and I spin it, can you tell that it's fun? No, why not? It's a sphere. Okay, it's spherical, it's symmetrical. Okay, how about the p orbital? Yeah, I can tell it's fun. There are different orientations associated with the p orbital and we can see that from the shape. Okay, so I get 3 orientations for the p orbital, only 1 orientation for the s. Which means when I go through and draw my diagram, I have to have those 3 extra orbitals shown in my diagram. Where's the next electron go in this drawing? Well, it needs to go to the lowest energy. Where's the lowest energy? 2p. Which 2p? Okay, the second one. No, it goes to the last one. Why? Good question. Why would it go there? No, this is where I get to be a jerk. What is the difference between the p orbitals? Nothing. There's absolutely no difference between those p orbitals, which means that next electron can go into any one of the empty orbitals. Doesn't matter which one. Okay, so I just decided to say it was that one. Am I right? No more right or wrong than you saying it went to the second one. Completely irrelevant. Where's the next one go?
Did it go to the first one?
Okay, so we want to start pairing?
No, I'm saying the second one. Did it go to the first one?
Oh, could the second one go to the first one? Let's go back and look at this, which is a really good question. What you're asking is that. Why no? Okay, Hund's rule. Awesome. We've got a name associated with it. You'll find that I hate names. Okay. Not your name. I love your name. Your names are great. I'll figure them out eventually. Okay. Why is that a bad thing? We just said the p orbitals are all equivalent. Why is that one a bad system?
Take more energy to keep those electrons next to each other.
Why does it take more energy? Didn't we just say they're all the same energy?
Because they're like
There's an electron on it.
electrons.
As soon as there's an electron there, what happened to the energy of that orbital? It increased ever so slightly, which then meant that first orbital is different in energy than the 2 empty ones. Okay? Do we ever address that in Gen Chem? Probably not. Okay. It's a very subtle difference in the energy, and it's enough that we could just go through and say, Hund's rule. Okay. Not a fan of that, but hey, it works. It gets us through that content faster. Okay. The next electron. Lowest energy, it's going to go to the empty 2p. It won't pair. The next electron. Now it starts to pair. Why does it not go up to the 3s? We have to fill the 2p first. Why do we fill the 2p first? Lower in energy. Okay? Why do organic chemists not really like looking at the third energy or higher? What happened to the gap in energy between the 1s to the 2s in comparison to the 2s to the 3s? It got smaller. What ends up happening the further up we go? Smaller and smaller gaps between those energies, which means the rule of lowest energy stops becoming a rule and starts becoming a suggestion. Okay? That makes it a little bit more tricky, and that's where we run into, well, there's an exception to the fill rate. After the 3p, sorry, remember organic chemists, numbers. 3p, what do we fill? 4s. Why not the 3d? Isn't the third energy level lower than the fourth? Yeah. Why do we jump to the 4s and not the 3d? Symmetry. The energy gap there is subtle enough that we get a better symmetric molecule by jumping into the 4s than the 3d. So symmetry plays a larger role the closer those energies get. Are these concepts going to come back and haunt us horribly through the semester? Yes. Right? So we have to be thinking about, first and foremost, the easiest level, energies. Treat your energy levels first. Then as we start to manipulate after that, we have to start considering, well, what happens when the energy is close? Do I now have to think about something else? Almost always yes. Okay? But start at the energy. And ideally, don't start with, sorry for whoever said it, Hund's rule. Okay? It's not that that's wrong, but you've removed your conceptual understanding of what's happening within it, and what I'm trying to get at is the conceptual understanding, not some old dead guy's name. Okay? Make sense? So when we get there, Markovnikov, Zaitsev, really old, really dead, didn't even know what an electron was, and yet we're naming reactions after them. Okay? Because they did some cool stuff. But beside the point. Okay? Understand why they're famous, what's going on behind it, not just the rule. Kind of make sense? Okay? So this is great. This is fantastic. We now could go through and define the electron configuration for every element on the periodic table, which you probably did in 151, and I don't want to do again. Okay? But all of that is virtually useless. Because what happens when we move into organic chemistry? This is the electron configuration for what? Carbon. Okay, fair answer. What carbon? A lone carbon? That's getting less sciencey than I wanted, but that works. A single carbon. Can I have a single carbon molecule? Technically, molecule is not a good word for it, because a molecule means two or more atoms. I'm looking at a single carbon atom. If I'm looking at organic chemistry, I'm looking at how carbon bonds to another atom, which means I'm looking at a molecule. Well, this was the electron configuration where the electrons existed for an atom, not a molecule. Which means virtually all of this is lost to us when we move up to molecules. And we have to adapt and use other rules, like hybridization theory. Okay? So these are the parts that we move from, but we have to have an understanding at the lowest level first. Okay? So what we just walked through were our extra steps here, our energy level splitting, electron pairs, all that kind of fun stuff. We could look at our diagrams. This is why when we look at the s orbital, there's only one orientation. There's only one s orbital. But the p orbital, I get 3 different orbitals because when I move that orbital on different axes, I can tell that it moved. So it has to do with the shapes. Right? Those shapes are probabilities. Right? So let's say, just because this was easy enough, it was kind of a joke, I take the probability sphere of one and I bring it near the probability sphere of another. What is the result of those two interacting? Should it be exactly the same? Okay. What happened in the intersection there? There's now a probability of finding the red electron. There's a probability of finding the blue electron. What's the probability of finding an electron in that space? It's greater. I've increased the probability of finding electrons between the atom, which means I now have a molecule because, what did I make? A bond. Okay? I would have to change my image now because that shape is really the probability sphere. Well, if the probability has increased here, I haven't shown that in my diagram. How could I change that? What has now happened? I'm now showing a larger percentage of finding the electrons between the nuclei. Okay? So we end up overlapping those percentages across. These are not static images. Okay? That's where this little blurry fuzzy thing came from. Trying to better represent that they're probabilities, not a solid shape. Kind of make sense? Okay. So, because this is OChem, we're going to simplify a lot of stuff. Largely because we're going to make a lot more stuff even more complicated. So we need to remove a bunch of things that are difficult. Okay, so on our walls we have periodic tables. This is the periodic table that shows up on your exam. What's different?
It's very small.
It's very small, yeah. We removed most of the elements from the periodic table. Okay, why? Organic chemists have very tiny brains. We can't deal with that. We have to have a smaller periodic table. Okay. That said, this periodic table is already giving me a headache because it's still too big. So I'm going to simplify it more. Okay. And arguably even within that, most of the time, I'm going to be spending my happy little life looking at only 4 elements. It's not to say I'm going to ignore the other ones, they do come in, but for the most part, that's where I spend my life, looking at those 4 elements and how can those 4 elements possibly change their interactions with the rest of the world. And in particular, how do they change their interactions with the rest of the world, being just the elements shown on that periodic table. Okay? So what patterns do we have in the periodic table that you can pull from what you remember of 151 for the large periodic table and then drop down to this periodic table? Do you remember any patterns? Electronegativity. Okay, I heard something about the electron affinity. You can forget that one, along with ionization energy. Gone. Don't worry about them. Okay? Because what do we do with electron affinity and ionization energy? We smash them together, average that stuff out, and we have electronegativity. Okay? Where electronegativity tells us as a general trend, fluorine is the most, and cesium. What the hell? I don't see any cesium on that table.
Potassium.
Thank you. Potassium is our least. All right? As a general trend, that works out great for us. That allows us to do a lot of simplifications that nail down nearly everything that we would manipulate. Okay? Because we don't, even though it's simplified, we don't want to spend our time memorizing the electronegativities for even this few elements. That said, there are 3 that I sort of have memorized? Which three?
Carbon.
Carbon's not a bad idea. So technically I have 4, but that's not one I'm telling you to memorize.
Hydrogen, fluorine, oxygen, nitrogen.
Damn it. So 5. Carbon and hydrogen I would get rid of.
Fluorine.
Fluorine, oxygen, nitrogen. Why fluorine, oxygen, and nitrogen? They are the most electronegative. They're our extreme. Okay? Where fluorine's the most, followed by oxygen, followed by nitrogen. Okay? That helps me when I go through to predict something about reactivity. Okay? And Lewis structure. Okay? Carbon and hydrogen I've only memorized because people have asked, well, what's a nonpolar covalent bond? Why are you labeling carbon hydrogen as nonpolar covalent? I go, I don't know, what the hell was the definition of that? Oh, you got to do some math subtraction. Oh, now I've done it enough times that I've memorized sort of their electronegativities. Close enough. Okay? But knowing the highest 3 are good. So electronegativity, we've got a trend for that. Okay? The symbol that I use for electronegativity, which is, from what I understand, the default symbol is chi. I think that's chi. Weird cursive looking X. What other patterns?
Ion shape, atom shape, or ion size and atom size?
Size I would go with. As far as atom versus ion, I don't memorize the differential between those. I just look at it as the atom itself. Okay? So when we look at size, okay, what can you tell me about the size? Somebody else?
Fluorine has the least or smallest.
Okay. Fluorine is the smallest. So any guesses from somebody else? Potassium's the biggest. Okay. Do we have any weird exceptions we need to worry about with size?
Hydrogen, really small.
Okay, hydrogen's really small, so as I go from hydrogen to potassium, okay, it should get bigger. Well, the trend makes sense. I agree with that. Okay, so hydrogen is really, really small.
And this is about size.
This is about size. Okay, how about let's go lithium to fluorine. This is another one of those fishing attempts. What happens to size as we go from lithium to fluorine? Okay. So this is a fun one that almost always confuses everybody because we have competing forces at play on this. Okay. If we look at explanations, so number 1, lithium going to fluorine. I heard a couple people saying it gets bigger. Why might it get bigger? What dictates size? The number of electrons. Our electrons dictate our size. So when I go lithium to fluorine, what happened to the number of electrons? It has more electrons, which means it should get bigger. Where do our electrons exist? I'll accept outside the nucleus. Keep going. Orbitals. Okay, and in particular, they go into the lowest energy level. The last electron for lithium goes into which energy level? The second energy level, which, getting more specifically, 2s. The last electron for fluorine, 2p being our orbital. What energy level was that? The second energy level, which means, are the electrons changing their distance from the nucleus? They're going to the exact same energy level. Size does not change. Just because I have more electrons does not mean I get bigger. I'm placing the electrons at the exact same energy level. What happens as I go down a column? They go to a higher energy level. That's why they're further from the nucleus. Okay? Were you taught lithium to fluorine stays the same size? No. Okay, so here's where I will jump in and be like, forget what you were taught. That doesn't mean you were wrong to be taught that. You were actually right. But for all intents and purposes, the size differential within a row is virtually nothing. Which means, what is the size difference between carbon and oxygen? Nothing. They're the same size. Okay? If I want an atom to make it into the warpy, zappy, blow-up thingy in Star Wars, the hole, right? Somebody get it? Okay, well, never mind.
I got it.
You got it? Okay, one person got it. Okay. I want a small thing to make it in the blow-up hole. Okay. Do I want to pick fluorine to shoot at the blow-up hole or bromine? Fluorine, because smaller. Fluorine or nitrogen? Doesn't matter. Okay, because as far as I care, they're the same size. I'll try and figure out what the blow-up hole thing was called correctly. Maybe I'll find a GIF. There we go. Okay, so that's the big change on size. Across a row, no difference. Okay, if you happen to say it gets smaller, that's okay. That is technically correct. But for our purposes, there's no differential there. Okay, what else should we know about our periodic table? Do we have anything else?
More metallic.
We could look at metallic characteristics, which is ultimately another expression of our electronegativity, so we don't have to stress about that. Okay, we could look at our orbitals. Boron through fluorine all fill what orbital last? The 2p. Everything over on our left-hand side is S. So we can start to do something with our orbitals as far as our organization goes. Make sense? Okay. So when we look at our periodic table, we're getting two pieces of information. Electronegativity, which tells us about the ability to grab electrons from somebody else. So it's telling us something about its reactivity, its energy. Size, we're telling us how big it is. Okay. If anybody's seen a 2-year-old running around, they have lots of energy. Right? If I gave a knife to a 2-year-old and let him run around a whole bunch, you're probably not all that concerned for your welfare. You might care about the 2-year-old and you might yell at me for having given a knife to the 2-year-old. But beside the point. If instead I lock you in a room, instead of with the 2-year-old with a knife, I lock you in there with me and a knife. Why are you now concerned more about me? Because I guarantee you that 2-year-old has a whole lot more energy than I do. Size. We're looking at competing things. Energy and size. They both contribute to organic chemistry. They both contribute to how an atom can interact with another atom. We need to be thinking about both and realize that they can lead us in different directions. Because if I take a 2-year-old that's hyped up on caffeine versus a 2-year-old that's only been fed flour, you're probably going to care more about the 2-year-old on caffeine. Okay? So we have to be thinking about both of those dynamics of what's changing, what's not. Make sense? Okay. So orbital, size, electronegativity. So now how do we move to compounds? Well, we're bringing these two atoms near each other and they generate some kind of interaction. Okay? That interaction is going to result in potentially two separate categories. Okay? One category, the electrons share. Meaning, we have some kind of bond. One category, the electrons come up and say, "Hi, how you doing? It's kind of cool. I'm going to hang out near you, but I don't like your nucleus. So I'm not going to share, I'm just going to be with you." Okay? We have an interaction now, but it's not a sharing interaction. So I end up with two categories that come out of that interaction. I get bonds and I get forces. Those two things are related to each other but mean entirely different things. Okay? What things are going to contribute to controlling that interaction? Okay, polarity could go there. You'll find that I hate the word polarity. We might have just talked about it. How about electronegativity? Okay. If I take fluorine as one atom and I bring it near hydrogen as the other, what happens? It's going to react. The fluorine will start to rip electrons away from the hydrogen. Okay. By definition, the hydrogen is now sharing those electrons across. I'm having a bond. But if I change the identity of that atom I can change that interaction. If I took fluorine and brought it near iodine, right, what's the difference now? Iodine is really, 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 really big. How tightly is it holding on to that outermost electron? Not so much. So what could happen? Our fluorine could go ahead and just rip it straight off. So we have to evaluate something about the size of our molecule as well as its energy to do something with that prediction. Right? And that's where we end up with our bonds, or what I'm calling here not bonds, which is ultimately a fancy way of saying, or not so fancy way of saying forces, or intermolecular forces. Okay, so what are our intramolecular attractions? Okay, ionic. Ionic is a good safe bet whenever we're talking about attractions, because ionic can fall under both categories. So we get ionic. What else do we have?
Polar, covalent, and covalent.
And I can tell you're cheating because you're looking at the slide, but that's fair.
That's what it actually.
That's okay. It's okay. It's okay. And our covalent. Most people will go through and add an extra word to the covalent. I imply it. Nonpolar is our definition on that, or our extra term. So when we're looking at the strength of our intermolecular attractions, we really have those three ones, which we would define as bonds. Okay? How do we know which bond I have? So for instance, if I take sodium and chloride, I heard a charge difference. It's a good option. Sodium and chloride, do you see a charge? No. So we could apply a difference in electronegativity. If I knew something about the electronegativity of sodium and chlorine and looked at that differential, I could then categorize it. How many of you memorized the electronegativity for sodium? Okay, I like it because that is the official definition. Our ionic is a difference in electronegativity greater than 1.7. But if I don't have the electronegativities memorized, that's a crap definition. A metal and a nonmetal. Okay. I apologize because earlier I said that ranking of metals and nonmetals, I said don't worry about that, I lied. You do need to know our difference between metals and nonmetals. Okay. Sodium is a metal because it's found to the left of our staircase. Chlorine's a nonmetal because it's found to the right. Right? So, new one. How about let's take a look at carbon and nitrogen. What is that one? Okay. So let's all get on the same page. If we call this covalent, what I hear is you're telling me nonpolar covalent. Okay. That's okay, but I just want to make sure that when you say covalent, that's, and then when I say covalent, I'm saying nonpolar covalent. It's a silent nonpolar. Okay. Is the carbon-nitrogen bond a nonpolar covalent bond? Sort of. Okay, where did you get the difference? So you're referencing a difference now?
Because the electronegativity of carbon is 2.5, I believe, and nitrogen is 2.
Nitrogen's not 2. So there's going to be our issue on that. So I was going to call you out for the I believe. How many of you memorized the electronegativities for carbon or nitrogen? Ouch. No, so the electronegativity, again, is a valid answer. That is the official definition for nonpolar covalent. It's a difference in electronegativity less than 0.5. But if you didn't memorize the electronegativities, you are SOL. Okay? What is our electronegativity definition for polar covalent? Yeah, somewhere in between. And there might be less than or equal signs in there too, I don't really know. Depending on who you talk to, you get different lines on those. So how do I decide what carbon to nitrogen is? It'd be nice if I had a rule of thumb like I did for the ionic, right? Okay. This is one of the things I find kind of silly because we talk about 151, 150. We talk about forces. Students should know that. They're awesome at it. It's because those teachers didn't teach OChem and realized that nobody remembered that because it made up such a small portion of what you were taught. And it didn't fit in any of the nice little buckets that you had to deal with as far as formulas and calculations that you didn't bother to memorize it. That's okay. We need a rule of thumb so that we can look at a structure and not have to spend every waking minute looking up electronegativities. 2 nonmetals. Awesome idea, except the polar covalent is also 2 nonmetals. So is the covalent. So that definition, while perfectly valid, doesn't distinguish between those two. Okay, if I take 2 atoms that are identical, I bond fluorine to fluorine, the difference in electronegativity by definition is less than 0.5. Okay? So the easiest definition for our nonpolar covalent would be same to same. Technically same atom to same atom, but I'm feeling lazy right now. Fine, so you're going to look at me like that. Okay? That works. Then that would mean polar covalent would be everything else. That's an awesome definition. Okay? That way all I have to do is memorize 2 definitions and the third one I get for free. Problem with this is that when we go into the real world and try to apply these definitions based on how these molecules would then interact with their environment, that we find a particular bond that would be classified as polar covalent according to this rule of thumb didn't work. And it acts more like a covalent bond. This being OChem, what bond might that be? Carbon to hydrogen. So a nonpolar covalent bond is same to same or carbon to hydrogen. If that is your bond, then you're nonpolar covalent. If it's a metal and a nonmetal, then it's ionic. Everything else is polar covalent. Okay? Not perfect, but those boxes cover about 95% of what you'll encounter. Okay, and let's see, on the very next slide I'll have the exception, right? Hopefully not. Kind of make sense? Okay. So now we've got a basic idea of what those bonds are. Let's put together some rules for how we do this. Because a significant portion of you already watched the Lewis structure video, okay, what we'll do is skip the rules, but I want the Lewis structure for sulfate. Okay. Spend a hot second here, draw the Lewis structure for sulfate. Everybody gets to do it. If I don't think you're doing it, I'll turn it into a quiz. It's supposed to be a quiz. Start with little anecdotes. Okay. You're probably told as a kid, go clean up your room. So you took all the stuff that looked like a mess and you shoved it all in the closet, closed the closet, right? Parents going, oh, yep, my room's clean. Then they open the closet and find a giant mess. Well, you did what was asked. You cleaned up the room. You just didn't clean it up the way they wanted you to clean it up. Guess what Lewis structure is? Okay. I'm the parent in this one. Okay. There's a very particular pattern that I want you to go through and follow when you draw Lewis structures. Okay? That patterning is there for a reason because it helps draw your attention to certain clues, okay? Like resonance. Okay? So almost invariably, this is what I started to see people go through and do. Okay? And right out of the gate, I'm yelling at myself. So, or yelling at you, you just couldn't hear me say it. Okay? So then another option, because a couple other people started doing this, and they're like, well, at least I didn't do that, so I'm okay. Again, I'm like, no, already losing my mind. Well, then what the hell do you want, Mike? Okay, this is why I had you watch that Lewis structure video, okay, and why there's a specific set of rules that follow that in the slides. You should be starting with identifying the valence electrons. Sulfur has how many valence? 6. Oxygen has how many valence? How many oxygens are there? Okay, and we also need to take into consideration the charge. It's a -2, so I have to add 2 more electrons to this. We're going to pause for a second. Okay, just because some of you are like, but I think I got the answer. Let's make you not have to wait. So you probably had something drawn out like this to varying extents, potentially. So this is one potential solve that we could potentially sit as saying accepted or correct. I'm not going to draw this other one all out. There's also this one. I lied. No, I'm not. I'm just dots like that all around the oxygens. Okay, so if anybody ended up with those, you're wrong. That's mean. Yeah, I know. 32. 32 electrons in our total. We'd pick our center atom, being sulfur. I would scatter my other atoms around it. One of the things that's nice about organic chemistry is the simplification. We stop at tetrahedral, which means 4. What shape has 4? Square. Place your atoms on the face of squares drawn around your center atom. You've got it set. Okay, we don't have to stress about anything else. Sorry, there's a box. There's stuff under there. Now we'd go through and place our electrons into the structure. I want 32 electrons. The first pair of electrons is going to go on oxygen. Which oxygen? Any of them, because they're all the same, just like those stupid p orbitals where I tried to be a jerk. You're like, no, we were too smart for that. Okay, I'm going to place it between the oxygen and the sulfur. Okay? Still, technically, I'm placing associated with the oxygen. I'm placing it there because I know I need electrons there because there's going to be a bond there. I'll place until I have 8 electrons around the oxygen because there's something called the octet rule. Octet for 8. I'll continue to place around my oxygens until I've achieved all my electrons. Have I achieved all my electrons now? Yes. Now that I've done so, I will erase pairs of electrons between atoms to make bonds. Okay? There's the lower right-hand structure. Okay? One of the last things that I would need to go through and do is assign or a check for octets. Do all atoms have 8 electrons around them? Yes. Even the sulfur. Those lines represented 2 electrons. Sulfur sharing them with oxygen, it has access to them. Every atom has 8 electrons. I have octets. The next step, which some people get in 151, and from what I've been told, some people don't, is assigning formal charge. Okay? The way that I would go through and assign formal charge is easier than your textbook would suggest because they want units. I don't want units, just tell me electrons. How many valence electrons does sulfur have? 6. How many bonds does sulfur currently have in my drawing? 4. How many non-bonding electrons are on that sulfur? Sorry, you said 0, right? I'm going to say yes. You just said 0. Okay, and we have +2. The charge on the sulfur is a +2. Oxygen comes in with how many valence? 6 minus, pick any oxygen you want, how many bonds? 1. Minus non-bonding electrons. How many non-bonding electrons are there? 6. This equals -1. Because all the oxygens are the same, this is why that lower right structure is incorrect. You've not specified the charges on the individual atoms. Are you responsible for assigning charges to atoms in OChem? Yes. Right? This structure is also incorrect because there's too much charge. Okay? Right? So one of the things that we ended up evaluating in Lewis structures, we move forward, is we say charge is inherently bad. That's why when I place electrons into electron orbitals, where do I place them? As close to the nucleus as possible, because the charges cancel out. It's lower in energy. So charge is bad. Every single atom in this structure has charge. So I want to cancel that charge. How could I cancel a positive charge? Give it electrons, say from a lone pair, from an atom somewhere nearby. So I can take the electrons from that bottommost oxygen and place them between the sulfur and the oxygen. The result being, I now have a pair of electrons between atoms. I can turn that into a line. If I go through and reevaluate my calculations for formal charge, I will find that that oxygen is now 6 minus 2 minus 4, neutral. The sulfur is now a +1. This is now a better Lewis structure than what I had drawn previously. It is still bad because I still have lots of charge. Okay? Can I get rid of the charge? Yeah. How could I get rid of that charge? Make a double bond for another oxygen. So I will go through and erase the lone pair. And there's a structure. If I go through and calculate charge, I still have charge in the molecule, but should I have charge? Yes. Sulfate is a -2. There should be a -2 overall charge on this. But I've gotten rid of one of the extra negatives and one of the positives. I'm now at as minimal a charge as possible. See, this is why I said the blue structure was wrong, because the blue structure and the structure I've drawn are different, right? So the structure I drew is clearly then correct because I drew it, right? What? Yeah, it's also wrong. Why is it wrong?
Shape could be different.
Don't accept shape. I didn't have to use those electrons. I could have used electrons from any two of the oxygens, which means there are lots of different ways that I could have drawn the structure for sulfate. Which means if I'm asked for the Lewis structure for sulfate, it's a nasty trick question, and I'm being asked to draw several structures. If I jump to the structure in blue, do I recognize that there's other solutions? Sometimes, maybe. Most of the times, not. By slowly drawing out your structure and placing the electrons first on the electronegative elements and recognizing why you're generating double bonds, you can find resonance possibilities. Otherwise, you're drawing the answer because you know the answer, which gets towards the homework. I will oftentimes get questions from students saying, well, can't I just do the questions in the back of the book? Yes, you can. Okay, well, why don't you assign them that way? Because what you'll do is look at the solutions manual. You'll be like, well, I want to check my work. I agree, you do. But what happens when you check your work? You've now looked at the answer. In Gen Chem, where the answer is 12 and you got 16, you go, well, I did something wrong. I'm going to go back and change my calculation to get to that answer. Okay? In OChem, you come up with a green pen, you check the answer, and it says red pen. Guess what you do? Oh, yeah, of course it's the red pen. I understand that now. Now I would get it right. No, you're still fundamentally wrong. Okay? And until you understand where you made the mistake between green and red, you have no clue what happened. But because you're looking at a structure that is the answer and everything about how you got to that answer is there in front of you, you don't make that bridging learning process. That's why the online homework system is there. Because guess what? You say the answer is a green pen, and it comes back and says, nope. You're like, well, okay, well, well, it's half a green pen. And it comes back and says, nope. Right? That's when you email me and I go, maybe you don't realize that the pen can change colors. You're like, what does that mean? And you go back and you look at your work and go, oh, it's not supposed to be, what did I say, green pen? It's supposed to be a red pen. Now I understand why. So now when I click it in, now I got the answer right. Because you've seen and made that connection. Okay? OChem answers are the answer. So whenever you look at the answers, unfortunately you have everything now about it. You can't now think back through it. Okay? That's one of the reasons why I use online homework. Okay? It sucks. Okay? Lots of times. Because it will come back and just tell you you're wrong. If it's a nice question, sometimes it'll tell you the hint that I would tell you. Maybe the pen can change colors. Okay? So here you could draw this structure and would be marked wrong. You'd be like, well, everything about my structure is correct. Yes, that one structure is correct, but you didn't answer the question. Draw the Lewis structure for sulfate. Sulfate requires all of the Lewis structures. Every resonant structure that is of equal energy. Does that suck to draw? Yes. That's why you get to do it. Okay? Because what that will do is help you learn how to draw resonance so that if you draw out this result, you can recognize how to change the blue structure to the red structure. For those of us playing ahead, how could we go through and do that? Well, if we look at resonance, it's all about moving electrons. So I look at that blue structure and I look at the red structure and I say I want them to match. For them to match, I need a double bond on that right-hand side, which means I need more electrons in that bond. So I need to move electrons to make that happy, okay? Or to make that happen. The electrons I'm going to move are going to be which electrons? Some of the valence electrons from oxygen. I like that. Okay. What about that structure makes you go, that's a valence electron? The dots mean there are electrons, not necessarily valence. Okay? That's kind of a freebie. Okay? Which dots?
The double dots.
Didn't I just move a pair of double dots? I can't do that. Ooh. Okay? There's a better answer here on that. I shouldn't do that. Where should I start my drawing? Identifying the most reactive electrons. What electrons are going to be the most reactive? Probably the ones where there's charge. So I will take the electrons from this oxygen and move them there. Okay. The sulfur was already happy with no charge. By moving that pair of electrons in, that means the sulfur now has too many electrons around it. So I need to fix that. I will fix that by breaking a bond. What bond in this structure do I want to break? The topmost double bond. Why am I picking the topmost double bond and not the bottom one? Yes, I'm trying to match the structure. Okay? Use the information you have. If we're going to match that, those electrons need to go somewhere. Where do they need to go? To the top oxygen. Why do they need to go to the top oxygen? Look at where we're trying to go. I need 3 pairs of electrons around it. How many do I currently have? Only 2. By having that drawing there, I can help see and push my way towards that. If I don't have access to that drawing, I'm then a little bit more stuck and I have to come up with other rules. Okay? So we will be doing resonance, drawing arrows and moving electrons when I have a target that I'm trying to match and when I don't have a target. You're responsible for both. You need practice at both. Okay? Where a lot of that comes into play is looking at the rules and drawing tons and tons, we'll skip that for a moment, tons and tons of Lewis structures. Okay? And we'll double back to this, I promise, through these slides in a little, not today. Okay? Doing tons of examples. And when you do those tons of examples, oh geez, I got to jump a bunch. What you're going to find is this. you're going to find some patterns. Remember the periodic table was simplified? This covers virtually every element that I said we needed to worry about. Okay? You will find that carbon, when it's neutral, has 4 bonds. Nitrogen, when it's neutral, has 3 bonds and a lone pair. Oxygen, 2 bonds and a lone pair. You will start to internalize these bonding patterns. Okay? How else could you internalize those? Print the slide, memorize it, backwards and forwards. Okay? Or do all the Lewis structures. Do tons of Lewis structure practice. The practice will be better than just the rote memorization because the practice will expose you to new questions that allow you to understand it and learn it better than the rote memorization. And I apologize. Yes, I know I talked a little too long.